Good evening. How is everyone doing tonight? We're going to be playing some Kahoot here in a moment. What we are doing is we are reviewing predictive modeling. What are some key terms in predictive modeling? Who knows what some key terms in predictive modeling are? Getting the Kahoot pulled up as we speak. A little short of a Kahoot, but some major stuff with some major concepts. Any words we might talk about in predictive modeling to start right here? What are some words we talk about? We need to know if it's quantitative or categorical. Always, all the time, quantitative, categorical. We're predicting a categorical X. Quantitative Y, quantitative X. Oh my gosh. This is the Y variable. This is train and holdout. The training data is what we create our model from. The holdout data is what we make predictions on. Different types of models like the linear model, the logistic model, the GLM net. Also, we've got some trees. What else do we have? We've got talking about the forest today. All different things going on. The naive is the basic model. Keywords right there that we're hearing. So lots of keywords like naive, GLM, GLM net, alpha, lambda, CP. What else do we have? mtry. So many keywords. Any of those words right there, I said a word, maybe like, what does that word mean? Start the Kahoot here in a half second. Did I say any words right there and you're like, I do not know what that word means, Brian? I do not know. I'm going to look at the Kahoot, make sure all the questions are looking good. Surely I said a word and someone was like, what word is that? What word did Brian say? Oh my God. We've got the tuning grid. Does everyone know what a tuning grid is? Gini coefficient. We've got entropy. What other words? Talking about like misses or things. What else do we have? What other words do we have? Overfitting. Any other keywords or words that you want explained right now? What words are there? IMP, variable importance. IMP, variable importance. RMSE, AUC. RMSE, typical miss. AUC, area under the ROC curve. Accuracy, what percent of the time does our model make accurate predictions? All this good stuff. I think it's looking good. Some tougher questions on the Kahoot that we will be reviewing right here. I think everything's good. Make sure I didn't make any changes. I think we will be good. Last few questions right here. Standard deviation. If the data has no value in it, no value? No, a few people have asked me about some data sets they're working with. Every data set people have asked about has a value that you're predicting. If a data has no value in it, like missingness. So Lulu right there asking, if a data has no value in it, is empty space, is empty data? If it has missingness, we might have to remove it or deal with the missingness or replace the missingness. But which ones are you wondering about there? We do have class tomorrow. We'll be reviewing class every day. Class all day, every day. Let's see right here. I think everything is good. Okay. The people leave job. People leave job? The people leave the job. Send me your question on Discord. Send me your question. I've been helping some people with their data sets, but let me know which one you're working with. All the data sets when we download them, but I've talked to a few people, helped them out, showed them where the data's at, and they're working with their data set with which one they're working with. Let me know which data set you're working with. Message me on either email or Discord, and we'll make sure your data set's working. But go ahead. Let's take a look right here. We're going to start up some Kahoot here. So let's get started on the Kahoot. Okay, it's time to review. Who is ready? Now you can go to kahoot.it. I think they want people to download the app now, but you don't have to. Kahoot.it. Go to kahoot.it. We've got Bronze Elk in here. And Lulu, message me. And Yaokui, if you don't have it too, message me also. If we cannot get a good model because of an outlier, can we just say that? Oh, definitely. Sierra, 100%. That's exactly what you should do. It depends. If the outlier is so crazy, then you might... Like, if it just looks like wrong data, then you can remove it. Like, if data is just wrong, data can be removed. But you can't remove data because you don't like it. You can't be like, I don't like this point. It hurts my model. But if it's drastically pulling the model away, you might be like, this one point... You can even add a categorical thing to be like outlier, not outlier. But I don't know. It's interesting. It all depends on the data, Sierra. Good question right there. So you would definitely mention it. Like there's talking about that one point and maybe examine it. Outliers require special attention. So that's exactly what you want to do. Who else? Let's put 1 minute on the clock. Join into the Kahoot right now. We got Focus Cheetah. A little shorter of a Kahoot, but with some big questions right here. And please ask those questions as we review right here and we go over the major concepts we've been talking about. So let me know. Good work. This is final report's pretty big one. Today during class, we talked about how to make some really great graphics. So make sure you check out today's class, today's office hours. We were going over how to make great tables, great reports, because the expectation is pretty high on the final project. So be making your final project look really excellent. We got just seconds to go right here. 23 seconds on the clock. Any other questions as we get started right here? Let me know your questions. We got Speedy Koala, Champion Bear, Green Elk. Big couple of days, I know, right? With 474, 475 finals. I'll be doing a lot of grading here in the next few days. Grades should be out by the weekend because there's going to be a good bit of grading going on. So we'll have grades up by the weekend. And with that, it is time to start the Kahoot. Let's do it. Here we go. Reviewing for the final. Oh, yes. 2 final projects. Lots of stuff. Good to see you here, Caitlin. If our model has an accuracy of 0.920 and a standard deviation on the accuracy of 0.025, what is a model that works just as well? What would be a model that works just as well? This is something we went over today in class. It's called the what rule. What would be a model that works just as well? It's called the what rule. Does anyone know in the chat? If you want to type the rule in the chat, we can look at the standard deviation, which is the measure of uncertainty. So standard deviation is kind of variation in the estimate. Now, why do we get a standard deviation? Kirsten, you're right. The one standard deviation, we're 100 points right now. So why do we get a standard deviation from the generalized RMSE or generalized accuracy? Why do we get that? So why do we get a standard deviation? What is the process by which we get the standard deviation and the estimate of the accuracy for our model? Here's a hint. Well, I generally use many of those. So what is the process by which we get multiple estimates of how our model does, and then there would be uncertainty or variation in that estimate? So just think about the process by which we would get this accuracy. So what process do we go through to get the accuracy, which then gives us some amount of variation in the estimate of how the model does? What process do we go through to get the accuracy? Very important to fitting your model. The accuracy is computed from the what? I usually use this many for it. I'll take a pause right here. The accuracy is usually computed from the what, which is our estimate of how the model does. The accuracy is usually computed, or the RMSE is usually computed from the what? How do we compute that? The accuracy or RMSE is usually computed from not the ROC. The ROC is its own thing. The generalization error, which is the what. Why am I holding up 5 right here? What does 5 mean? Usually in the codes, think about the code. When you say 5, number 5, the generalization error is the what? It's the what thing that we do? 5? K-fold cross-validation, exactly. And usually we use 5. You don't have to use 5. But think about this. If you make 5 estimates, then how would you figure out what your accuracy is from the 5 estimates? Theoretically, if you have 5 estimates of how the data does, what would you do with these 5 estimates to get the estimate of the accuracy right here? So when you fit the model, you get 5 estimates of the accuracy. So what would you do with the 5 estimates of the accuracy to get your accuracy estimate? These are your 5 estimates. What would you do with these 5 estimates? You would average them. So when the K-fold process does it, it's going to take the average of your 5 estimates. Now, the 5 estimates will have what in them? They will have, think of a V word, which standard deviation stands for. The 5 estimates, they won't all probably be 0.92, 0.92, 0.92, 0.92. When you're estimating how your model does, they'll have variation. Great job, Kirsten, right there. More points, everybody. So they'll have variation. So sometimes your model does a little bit better. Sometimes your model does a little bit worse, depending on which of the 5 folds it was predicting on. And so with that, your model might be this good, or it might not be this good. So when we say a model that works just as well, we're asking a model that is 1 standard deviation less. So if you look at the math right here, 0.92 minus 1 standard deviation is going to be this right here. And so we want a model that works just as well within 1 standard deviation of the best. And that's called the 1 standard deviation rule. And we can pick the best model, but any model within one standard deviation is kind of like, well, so you could do an upper bound. Like when you get your model, any sort of plus or minus one standard deviation are models that are similar. Does that make sense, Preston? Great question right there. So if you get your model, any model within one standard deviation is about the same as your model. Now, when you think about a model that works just as well, I guess technically we should also include the upper bound, but a lot of times we consider the lower bound on what's going on because this model right here, so technically yellow could kind of be an answer too. But if you're considering other models, and this is like your best model right here, you would generally think any model within one standard deviation below. But you can obviously say models within one standard deviation are nearly identical. Yeah, so it's kind of right-ish, but in Mackenzie, 100 points right there. That would be a model that it works just as well, so I guess it's kind of right. It should have been multi-select, right? Where can we find Statistics 1's lectures? Check out the channel, Bayram. Good to see you here. If you click the videos, you can type in the little box up there, the little question box right there, and you can find almost any video on a lot of topics. Good to see you here. Mubot saying, hey, they're really in the chat. Thank you for swinging by. Let me know if you can't find something. We'll help out after the Kahoot right here. Good to see you here. So let's see. Soaring Yak in the lead. Focus Cheetah, Champion Bear, Dandy Sea Lion, and Rational Koala. Who's going to win? Let's find out. How many models are being considered right here with this expand grid? So the expand grid makes the models. It's the tuning grid right here. This is a forest grid. You're welcome, Bear. I'm so good to have you here. Let's throw 100 points to the chat. Thank you for swinging by. Depends on what topic you're looking for. I've covered a lot of topics. Check out the playlist also if you're still listening. Check out the playlist. There's playlists on different chapters. So what is M-try? Does anyone remember today what M-try is? M stands for the number of predictors that we're going to what? How would you explain to someone what M-try is and what it means in a forest? This is from today's lecture. But then also we have to know kind of what goes on with an expand grid. So what does M-try mean? So when you make a forest and you get to a node right here and it's going to split, this is the number of what it will consider at that node. So when it gets to a node, it's going to say, I will consider what? The number of predictors, exactly. So if you set M-try to 1, it's going to force in some of the predictors each time. It's going to get to this node and say, I've got 20 predictors. I have to use this one. If it gets to the node with M-try 4, it's going to say, of the 20 predictors, here's the 4 that are randomly selected, and I'm going to choose from splitting on based on these 4. Now, why is the answer here 2? Well, this is, what does this mean in R right here? It says M-try has values. So we're creating what is called an expand grid, which will do all the combinations of the different tuning parameters we put in here. And we're storing it into forest grid. So tell me it's just 1 and 4. That's all that vector is. It's 1 and 4. So there's 2 possible values. So all it is let's try M-try 1. Let's try M-try 4. Now, what if we had down here and we were to go, and I swear we used to be able to do number of trees. What if we took this and we added a second thing in here? So you got to pretend we're putting a comma, and we put n tree, and we did equals concatenate 100, 200, 300. So now, how many models would be created now? How many models would we be considering if we had a second argument in that expand grid? And I'll start writing the expand grid for you right here. I think not 5. Good guess. Not 5. So I'm writing out the expand grid over here on the side. This is what the expand grid would look like. So what does the expand grid do? The expand grid, oh, there we go. Wrong value. No, that's right value. The expand grid does what to the variables we give? The expand grid does all combinations. So you can see right here the 6 combinations. Does that make sense? There's 6 possible combinations because it kind of permeates through. So if you have 2 right here and 3 right here, 2 times 3 is equal to 6. And so there we go. That's how many No, don't worry. KP 100 points. Good practice right there. Good memorizing, good memory. We practice, we get better as we do it. But the expand grid does all possible combinations of tuning parameters. Why do we do tuning parameters? To try to do what? Why do we do this whole tuning parameter thing? Because the cool thing is we can just make tons of whats and try to find the what one. Like, why do we do tuning parameters? What's the point of a tuning parameter? They're the amount of predictors that are tried at each node to test different models, to test different ways of doing it, because the forest can be constructed different ways, and the amount of predictors we try at each node, like the forest is going to do that for us. It's going to get to a node and say, I can only use one of these 20 predictors if we have 20 X's. And so it's going to try just one. Now, there might be a better one that it didn't get to use. So that's why we could turn up the mtry and say, okay, now you can try 14 of the predictors out of the 20 at this and see which one is best and choose the split from there. But lowering the mtry, no worries. So set to one. If you're in set to one, email me and I'll once again thank you. Yeah, go to the playlists and check out where it says like test one material. Go to test one material. Meebot saying hey to everybody. Go to test one material in the playlist. I can also show you at the end if you'd like. Don't worry. Good questions right there, Bayram. Good to see you here. Let me know if you can't find it. But basically, we have a playlist for test one and stuff like that. Test one material, stats to a one. Good work right there. We got Soaring Yak in the lead. Next question. Let's do it. A leaf in a partition model has the following y variables. Compute the Gini. Following values. What is the Gini coefficient? So Gini is a measure of impurity. Pretty quick question, but there are values that are impossible right here. You can narrow it down pretty quickly to some impossible values. Gini and entropy are measures of impurity. Only 2 people got it right. So what is the maximum Gini coefficient? What is the maximum Gini coefficient? What is the maximum Gini coefficient? Now, there's a few ways to answer this. What is the maximum Gini coefficient? What is the maximum Gini coefficient? The highest Gini coefficient can be is what? This is last week, I think Thursday we're doing this, or Friday. What is the maximum Gini coefficient? Gini is a measure of impurity. The maximum is 1. And actually, we can't even achieve that with 2-class summary. The maximum Gini coefficient would be what? With 2-class summary right here, and let's show it. The calculation of Gini is 1 minus, and then we put right here, A over total squared plus B over total squared. There it is right there. It's in the notes. We were practicing a little bit last week. So if we were to have the worst possible, think about what the worst possible would be. The worst possible with 100 observations would be what? What of the A class and what of the B class? What is the worst impurity we could have? Like just amount for A and B. What is the most impure it could be? So the least kind of sorted, the most impure it could be is what? What is the most impure a leaf could be with 100 observations? The most impure it could be is what? What is the most impure with 100 observations? So 100, but how so? Or not 100? Well, so how so? What is the most impure it could be? So basically, you've got red balls and blue balls, and you're trying to sort them. And so you've got a box, and what is the most impure with red and blue it could be? It could be what? So what's the most impure it could be? Like you're like, this is all not sorted right here. What's the least sorted the red and the blue balls could be if you're trying to put them into one box, like one group to themselves? The most impure they could be. Well, so how many red balls would be in there and how many blue balls if it's completely impure, as we would say? How many red and how many blue? There's 100, equally split. So what would it be? With 100, that would be what? So with 100, that would be what? So equally split, right? So the amount of, it'd be 50-50. Great job, Chanel, right there, and great job, Preston. Good work, and good work, Kayla and Riley. It'd be 50-50. So what is this? This is 1/2 squared plus 1/2 squared. And that is actually equal to 1/2. So this is 1 minus 1/2. And the worst the Gini coefficient can be, and we talked about this in class, The worst the Gini coefficient can be for a two-class summary is what? What is the worst a Gini coefficient could be for a two-class summary? For two-class summary, the worst the Gini coefficient could be is 50% right there, or 0.50. So the worst it can be is 0.5. And so when you think about this right here, what do we have in our problem? Our problem looks the following way. Our problem right here is 4 observations. And with the 4 observations, we have here 1 out of 4 here. And then we have, well, it's going to just be that right there. So 1/4 squared is, that's 1/16. 1/16 and 9/16, and that's 10/16, and that is equal to 6/16, which is 0.375 right there. So 6/16. And what is the best we could do? Think about this. If this was actually a no class right here, what would the Gini coefficient be now? This one's much easier to solve. If that was a no class right there, what would the Gini coefficient be now? If that was a no, and just think about why it is this. Think about what it means that it is this. It'd be 0. And the Gini, because what does that mean if your leaf ends up that way? If your leaf ends up that way, what is the theory behind that? Well, we have all no class, no yes class, that's that, that's that, that's that, and that's that. What does that mean that the Gini coefficient is 0? It means that that is 100% water. Basically, there's no impurity, exactly. There's kind of variance. You might say variance. Because impurity is variance. So we'd say there's no impurity. Great work right there, Mackenzie, and good practice. Just understanding why the values turn out this way. It's pure, exactly. The impurity, there is no impurity. So Gini coefficient ranges from 0 to 1. There are upper limits with the amount of class summary we're doing. For a 3-class summary, it's 0.66. 4-class summary, 0.75. It's just actually, if you do 1 minus 1 over, because when you do the mathematics, it turns out that way. Like, if you do a 10-class summary, what would be the maximum impurity for 1,000 points? I've never put a test question like this, but with a 10-class summary, what is the maximum impurity? I'm wondering if anyone caught on. For 1,000 points, with a 10-class summary, what would be the maximum impurity? With a 10-class summary, which would be pretty crazy, it'd be multinomial stuff. 10-class summary, the maximum impurity would be what? Did anyone figure it out? I'll give 100 points for a guess, but 10,000 for, or 1,000 for right answer. 10,000, come on, Brian. Not, so Gini, Kirsten, that's correct. Gini can only range between 0 and 1. Gini can only be between 0 and 1. And then the possibilities of the upper level of impurity, I guess like as you go towards infinity classes, that's when Gini gets towards 1. But Gini actually never hits 1 until you hit like infinite classes, and that's like infinitely impure, which is kind of an odd thing to say. Like it's pure impurity, which would be weird. But does that make sense right there? The mathematics for it would be 1 minus 1/10 plus 1/10 squared 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 would equal up to 1 minus 1/10. And so because they would all be 1 over 100 and you'd have 10 of them. So anyways, a little fun math right there. Next question, who's in the lead? Dandy Sea Lion, Soaring Yak, Stone Lead, Speedy Koala, Rational Koala. All the koalas are here. And Champion Bear. Here we go. Multi-select. We like the multi-selects. Which of the following allows us to analyze categorical variables? Love it. Okay, categorical variables can be done with which of the following? I'll give you a hint at 10 seconds. Hint is coming up. Your hint is there's only one wrong answer. There's some keywords on here you should see. Linear models are called what? Starts with an R. They're what models? Well, there it is right there. Linear models are regression models, and this is a quantitative Y. But here's the thing. GLM, which is the generalized linear model, can also do what kind of regression? GLM, which is the generalized linear model, that does not say GLM. That doesn't say generalized. That just says linear regression. But the idea of generalized, great job, Mackenzie, it can do categorical because generalized also means logistic right there. So generalized encompasses the idea of linear and logistic. So it can do more things. So that's why we don't use LM, which is just linear model. we use the generalized linear model, which is a global idea for both the logistic curve and the linear curve, which is a line. Gradient boosted models were at the end of class today. I took all the questions off the test on them on gradient boosted models, but it's good to know. And there's a Kahoot, little bonus right there. Partition models and classification trees. Partition models, maybe using some forests, but they're another form of classification trees. So good stuff, good answers. Let's see who's in the lead. Leaderboard's going crazy. Soaring Yak and Dandy Sea Lion. Whew. Focus Cheetah. You got this. Here we go. Achieving 100% accuracy on a training subset would be an issue with what? Maybe you just got a really good model, right? I mean, maybe someone would be like, I think I'm fine. 100% accuracy. 100% accuracy. What would that be an issue with? You're like, I got 100% accuracy, Brian. My model works perfectly. Perfectly predicts everyone. I might say, well, what's the AUC? It would be overfitting. I think people get that right there. So how do we guard against overfitting? Like, what do we do to guard against overfitting? How do we make sure we don't overfit? Like, and you have to do this for your project. You have to make it clear. You have to really communicate in your model selection that you've done this. Well, cross-validation is how we pick our model. So the point of cross-validation is to estimate how we'll do. So the cross-validation is like, I think I'll do this well. And then the holdout, as Kayla's pointing out right there, the holdout is I have not overfit. My model actually works on new data. So you have to do, and what code do we have in R that we need to run and need to communicate the results of? What code do we need to run that is going to see how we do from our predictions on the holdout? There's lots of ways to do it. Quickest way is with this code right here, something resample. Does anyone know the code that we can do to look at our predictions versus the actuals and then just compare them like that? We can look at our data and see how we did. Post resample, Preston got right there exactly. KP, Riley, and Preston. That's going to just take your predictions from your model. So you put your predictions. Usually I like to save it if you watch when I do it during office hours sometimes. I take my predictions, store them into predictions. Then I do post resample of my predictions, comma, the Y vector of the actual in the data set. So usually hold out $sign in the Y value. So make sure you get your predictions from your model and then you get your actual. We got the gradient boosted to work at the end of class. It was pretty cool. So check that out. Not required, but I love those models. And it actually had the best and did well on the holdout. So I'm just saying gradient boosted, pretty powerful. Leaderboard's shaking up a little bit. Soaring Yak and Dandy Sea Lion still in the lead, but good to see you here. Rational Koala and Radiant Bunny. We love bunnies here. Which of the following describes a complex logistic regression model? So when would a logistic regression model be complex? I think one of these answers is a little bit mean, but I promise it's not literally what it says it is. You might say, well, doesn't it say that? And I'd say, well, cost parameters for support vector machine. So don't answer cost parameter. Support vector machine is not on the test. The second most answer, I think people thought it was like a trick question. What is complexity parameter for? When do we use complexity parameter? The complexity parameter goes to what idea? When do we use the complexity parameter? When is complexity parameter? Well, we use it for the grid, but when do we use the complexity parameter? Complexity parameter is used to determine what? How much we do what? The complexity parameter right here is used to determine what? When do we do a complexity parameter? A lot of stuff from today's lecture. No worries, Roberto. Good to see you here. Yeah, we have it up here in a second. We'll put the code up. So when do we use the complexity parameter? How big the tree is. Great job, Peaks, right there. So the complexity parameter controls how large the tree grows. So when you have a higher complexity parameter, you actually get simpler trees. So what if you set your complexity parameter too high? Your tree would never do what? If you set your complexity parameter too high, your tree would never do what? Like if you take the complexity parameter and bring it all the way up, and you say, I'm going to have to make a perfect model on one split. It will never split. So you'd actually get the what model. If you say, I want 100% reduction in impurity or 100% increase in R squared, well, I guess either you're going to get a perfect model immediately or you'll get the what. How do you talk about in the project guard against overfitting? By comparing your train and your holdout, the ratio. That means you've probably not overfit. Like if your holdout works about the same, you probably have an overfit. to the project, Preston. Good question. And so you probably are going to be stuck with the what model here because this is not going to split. You're probably stuck with the what model here because this won't split. It's gonna say no to splitting. You're just gonna get stuck with the base model right here. So you're probably working with the what afterwards. Probably the naive, exactly, which would predict the majority level for everybody. And that's, well, if we're doing impurity, majority level. If we're doing quantitative, it would predict the what for everybody. If we're doing quantitative, it would predict the what for everybody. So the naive would predict the what for everybody if we're doing a quantitative tree. If we're doing a quantitative tree, it wouldn't predict the majority level. It'd predict the mean for the whole data set. And leaves are where we do the prediction of the mean. Like within a leaf, we predict the mean for that group. But if we're not splitting the tree, then it's everybody. So it's still kind of the idea of in linear regression, the mean is the naive model. But if we have a logistic model, it's the majority level. So just understanding the idea of what the naive is, that the naive either predicts the majority level or predicts the mean. Both of these right here are the naive model predicting the mean for the leaf or the mean or the majority level for the leaf. And once again, if the tree never splits, then it just predicts the mean for everybody or the majority level. Like if this tree never split right here, what would the naive model predict? What would the naive model predict? If this tree never did any of this splitting, what would the naive model predict? The naive model would predict what if it never split? It'd say everything's a triangle. Say pretty much all 60% are triangles. Cool, everything's a triangle. Does that make sense? So we just look at majority level right here and say that's the prediction. If it never split. Now, when it gets down here to the bottom, it actually classifies, if you think down here, this tree has achieved what percent impurity at the end. At the end of this, the tree has achieved what percent impurity, which is why it kept splitting. At the end of this tree, it has achieved what percent impurity, and just look the way it look at the way it looks. I see dots in one leaf, I see triangles in another, I see triangles in the next, and I see dots in the last. The impurity is at 0%. It's actually minimized impurity 100%, which is the goal of the tree, is to kind of sort things out or put things with the same mean together. So the tree is doing extremely well in this example, and that's what we like to see. So complexity parameters are for trees. Lots of predictors would be a very complex logistic model. And how can we guard against lots of predictors? Because if we just let the equation try to minimize the sums of the squared error, we're going to have a problem. So how with logistic regression can we guard against getting lots of predictors? I'd love it if that was just an essay. Logistic regression, can we guard against getting lots of predictors? How with logistic regression, I was thinking about adding it right there, and I was like, I've got too many things to grade. I was like, I'll just take the test being the way it is. How with logistic regression can we guard against getting lots of predictors? So what do we have to guard ourselves? Regularization, literally, that's it right there. And that's what regularization is. Great job, Kayla and Kirsten. Regularization is going to penalize us for taking information from the coefficients. So the larger the coefficients, the more we use them, the more penalty we have. And so we can create that grid right there that says, maybe let's put a big penalty, a big lambda on there, not lambda from 475, but let's put a big penalty on how much information we take. Next question and good review, everybody. Dandy Sea Lining the lead. Soaring Yak, no, but Focus Cheetah right there. Calculate the AUC. Really tough question, but think about the theory behind AUC, and you could probably figure this out pretty quickly. I think there's only maybe even two viable choices on the screen. AUC is the percent of time we give the yes and the no's proper placement. And if you're very quick, you can get it really quick right here. Let me ask you the following question. Just answer in the chat. This yes right here received a higher probability than what percent of the no's? This yes right here received a higher probability than what percent of the no's? That yes right there, this one right here, what percent of the time was it higher than the no's? What percent of the time was this yes higher than the no's? Just this one. So I've got it ordered, 100%. How about this one? 100%. How about this one? 75%. So how about... There's the answer. Of course, that's a decimal. So it should be third of 25 minus 100, and there it is right there. It should be 91.67. Good work. Wow. Actually very impressed that many people got it. So really the worst AUC we should generally see by a random guess model would be what? when you have a random guess model that really doesn't know what it's doing, and it just randomly sorts the yeses and nos, it almost looks like it. If you had a random guess model that's just randomly sorting the yeses and the nos, then kind of what would we expect from that? Just think like it's random that a yes or no would get a higher probability than each other. It's just like yes, no, no, yes, no, yes, 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 no, yes, no, yes. Oh yeah, we'll show right here, KP. We'll show it here in a second too. Yeah, we'll show the calculation again. No, we'll go over it. With the random guess model, what would a random guess model have for an AUC? 50%. Because when you go through your true negatives and your true positives, you'd probably go through them equally. So what you want is when you go through your true negatives and true positives, which are what things actually are, you want to go through your what's first in your list. If you're going through your data, you'd want to go through your what in your data first. Your true positives, like if you have a list sorted right here by yeses and nos, and I think it was yes, yes, no, yes, no, no, no. If you were to go through your data, those are the yeses, 2 yeses at the top, a no, and then a yes right here. How would you want your data sorted? How would you want your data sorted? You'd want to go through your what's first. And the yeses are also known as your what's. Your yeses in the data, are they your true positives or true negatives? Are your yeses your true positives or your true negatives? And this is what people actually did, like if they actually bought the house. True positives. So if we were to make this into a grid, it might look a little bit odd here. We have 1, 2, and there's the 3. Good. And then we go over here and we go 1. We'll try to make it even. Let's do that. 1, 2, 3, 4. Okay. So these are my true negatives, true positives. Here's the random guess model. And that's kind of the worst we could do in a lot of instances. Like random guess models would be about a 50-50. So when you look at this right here, if we have a yes on this grid, I should do what right here? If we have a yes, should I go up or should I go to the right? I should go up, right? So going up means we went through a true positive. Now I should go up right here again. And I'm talking about this right here because we're going through these. So that's an up. Now we get over here to the no. And we go to the right. Now we go to the yes, and we go up again. Because all we're doing is going up if we go through a true positive, or to the right if we go through a true negative. Now we go to the right 3 times. And I'd like for you to tell me, how many blocks are there on this grid? Just take a look at this grid right here and tell me how many blocks are there on this grid total. So how many blocks are there on that grid? So how many blocks are there total on that grid? And then let me shade it in. Is there 11? I don't think there's 11. Everyone's saying 11. Oh, I see why you're saying 11. Yes, there's 12 total, but I'm shading in 11. I get that there's 11, right? And that's 11 twelfths. So we should get, if we do 11 twelfths, there it is right there. There's the AUC. There's the area under the curve. But you might say, well, Brian, you did it a little bit more quickly. Well, AUC is the percent of time the yes class gets a higher probability than the no class. Remember, this has been ordered so that we went by probabilities, with the highest probability being at the top and the lowest probability being at the bottom. If you look at this singular yes class right here, what percent of the time does it have a higher probability than the no classes down here? That singular yes class right there, what percent of the time does it have a higher probability than the no classes? Like you'd say, like, okay, that's at the top. What percent of the time does it have a higher probability? 100% of the time, right? So the first one is 100%. And then the next one, what percent of the time does this yes class have a higher probability than the no classes? What percent of the time does that yes class right there have a higher probability than the no classes? Just looking at it visually, like 100% again, right? And then you go to here and you say, okay, wait. This one only, how is it 100? Because so right here for the one we just did a second ago, this yes class right here is higher than 4 out of 4. Does that make sense? It's higher than this one, this one, this one, and this one. It's higher than 4 out of 4 no's. This one, and Yakui, great job right there, 100 points. This one is higher out of 3 out of 4 no's. So this one has 75%. Does that make sense to say that it's higher than 75% of the no's? Do you see like there's 3 no's below it? So there's 3 no's below it, and there's only 1 above it. Does that make sense, KP, right there? This one right here that we're talking about is this one right here. It's higher than 75% of the no's. That's when we say 75%, we're saying this is higher. This yes right here, which corresponds to this probability, got a higher probability than 75% of the no's. How's that sound? So you work your way through all the true positives through the process, correct. So if you look at all the true positives, you can say what percent of the time did this true positive get a higher? So it's an iterative process. This is why we don't do it by hand. Also, the curve can be drawn for us, but understanding what it's doing is important. That this value tells us 91.66% of the time the yes class got a higher probability than the no class. So now that we did this for 3 yeses, what should we divide this by? Now that we did this for 3 yeses, let's divide by 3. And that's it right there. You could also do the same sort of calculations. We'll go 100 plus 100 plus 75 divided by 3. Another way to calculate it right here would be to say, you could just simply tally it up. You could say this top yes right here is yes, 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 yes. And then the next one is also yes, 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 yes. The next one is going to be no, because we're looking at this one right now. It was not higher than the first one. Yes, yes, yes. And if you look at this, what do you get mathematically here? So hopefully seeing the multiple ways to calculate it, what does this mathematically equal to for the percent of yeses? And that's when yes was higher than no. And I'll put some breaks in here. This was your first yes. So that's the first yes. Second yes was higher than all of them. And third yes was not higher than the first. So what would that equal to right there? Yeah, exactly. I like seeing it. It's like, hopefully it makes sense. Yeah, Chanel, good, Kayla, good to see it this way. Just solving it a few different ways, seeing it with the grid, because you get the AUC visualization, but then also seeing it a little bit here. Down here, this mathematically equals to 11 out of 12. It's going to do the same calculation over there. But I don't want it to be magic numbers, because someone just says, oh, the AUC is this. And you're like, if you actually see this, oh, good job, Preston. So glad this is helping everyone kind of understand it better. I know we're hitting you with a lot of information. Sometimes I've had people take this class and be like, I never even knew what AUC was until you explained it. Maybe they still don't understand. Maybe they're just being nice to me. But it means a lot when someone's like, yeah, I've heard this term thrown around a whole bunch. What's it actually mean? So we want to do some simple calculations of it, and then we'll let the computer do the complex one and show us the really crazy stuff and do all the big stuff. But we should have a basic understanding of what's going on right here. The easiest AUC calculation, you can. There's multiple right ways to do it. But the most gimme AUC problem I could ask you, the easiest one I could ask you, is this. What is the AUC now? I changed that yes to a no. What is the AUC now? And that you should see this and be like this. It just should be instantaneous almost, hopefully. If you know how to do AUC, you can look at that and say, yeah, 100%, yeah, it's 1. 100%. So, because the yes always has a higher probability than the no class. So that's where hopefully, we don't have to do a lot like calculating AUC by hand. But if you understand what AUC is, and if someone says I have an AUC of 100%, the yes class must always have a higher probability than the no class. What is the accuracy of this model? You can tell me as a fraction. I can kind of think about it. It's like 85 something. The last half. It's the last half. Good question right there, Peaks. The last half. So what would be the accuracy of this model? Yeah, it's 85 point something. Yeah, or you can just tell me as a fraction. The accuracy of this model would be what? What is the accuracy of this model? Or you can tell me misclassification rate too. What is the accuracy of this model? Accuracy is the amount of time that we correctly classify. 85.767, yep. Because like 14.28 is a seventh, so 100 minus 14.28. Sevenths are interesting because 14.28, I think it's like 5. Yeah, they're pretty cool. And that's where we misclassify right there. So that's the Does that make sense? So the model has an accuracy of 6/7 or 85.7%. The model has an AUC of 100%. Just understanding what these metrics are. And this only applies to a Y that is what? Accuracy and AUC only apply to a Y variable that is what? Accuracy and AUC only apply to a y variable that is what? Which means you need to set up your fit control properly. Categorical KP, you got it. So make sure that fit control is properly set up. Mebot loving the cats in the chat right there. Let's see who's in the lead. Oh my gosh, Sturdy Snail and Bronze Out. Good to see here. So if it was still the yes, then I think so, right? Let me see that again. Oh, great job. Another 100 points. Excellent work. You are right. That'd be 5/7. Good job, Kayla, right there. That'd be 5/7 because there you go. And this is the original problem, accuracy of 5/7. Good work. Good follow-up question. We're going to throw 1,000 points as we ask the next question right here. Kayla, such a good question. Multi-select. Which of the following does logistic regression use to measure how the model works? Should be a review question. 1,000 points, Kayla. Multi-select. Give a pause right here. Now, 2 of these are kind of identical. You can answer them both. There's 3 right answers. There's 1 wrong answer. I like to give hints as we do it. The only wrong answer is a whole different class of error based on error. The sums of the squared error. Now, misclassification is the complement of what? If I say the misclassification rate, it's the complement of what, which means 1 minus this. Misclassification and what are complements of each other. So you can talk about the misclassification, like what it means of accuracy, exactly. So these are just complements. If accuracy is 85% or something, then misclassification is 15%. You either accurately classify or misclassify stuff. So that's just those 2 are same metric. AUC is what we just talked about a moment ago. But sums of squared error means y must be what? If you hear sums of the squared error, y must be a what variable? If you ever hear we're doing a sum of a squared error, think you have to square it. So what does that inherently mean about y? It means it's numeric. So that's where you're doing RMSE, MASE, MAPE, MAE, MAE, all those right there. Now you can use AIC for all of these. AIC is how close our model is to the truth, and the lower the AIC, the better. So you can use AIC or AICC for any of these. That's how close our model is to truth, and it works for categorical or quantitative models. Let's see who's in the lead right here. Leaderboard's going crazy. It really is anyone's game. And once again, $30 first prize, $20 second prize, $10 third prize. Who's going to win? I think the 475 winner hasn't emailed me yet. I'm interested to know who it is. It's really cool to see who wins these. I love it. You get shocked sometimes. You're like, whoa. It's really cool. Next question. Let's do this. Which of the following represents the typical miss the model makes? We should know this like that. Which of these represents the typical miss the model makes? Oh, yeah, you're supposed to, yeah. Might have found the winner. Yep, email me and I'll send you the gift card. You get the gift card if you win. Glad I mentioned that. Oh, no worries. Yeah, we give winners. Yeah. If you're, for first, I think second, third email me from the 475. Yeah, I think that got emailed. I think. You could Discord me too if you wanted. Either one works. Email works too, because then it's easier for me to click your email then. And then I just go to your email, I go to Amazon, I send you the gift card, and boom. But yeah, please email me if you win. First place, $30. Second place, $20. Third place, $10. Just my little... We make not a ton of money off the YouTube channel. I think I know this might sound like a lot. I think I made like $1,500 from YouTube altogether, all the time I've been on YouTube. And I've been on YouTube for a decade. Yeah, $150 a year. Preston's like, I won the 475 Discord. I mean, the 475 Kahoot. Like, you're in the class, Preston? What? The typical miss the model makes is RMSE. Benson, good to see you here. There it is right there. Money bags with that $150 a year. There it is right there, Benson. Well, we weren't monetized to begin with, but we make like $400 a year, but we give it away in Kahoots and stuff like that. So not trying to make the big bucks on YouTube. And if you notice, obviously we don't monetize class videos. It's just some of the help videos go out to a wider audience. Never hit the algorithm on anything. Got some 30,000 views videos, but it's been up for a while. Next question. Let's do this. Bronze out, focus to Sturdy Snail. You got this. Takedown, Soaring and Yak and Dandy Sea Lion. I do like Dandy Sea Lion's name though, so I'm rooting for you. Here we are with the next question. Multi-select EBK earnings before Kahoot. That is very true. Which of the following model Natural, which of the following naturally uses interactions? Naturally. You don't have to do anything special. They can all use interactions technically. But some of these, more recent models we've been talking about, naturally incorporate interactions for us, which can go to overfitting. So we can run into problems, so you really want to make sure you have a holdout. We talked a lot about holdouts. We talk about holdouts like every day. Every day we're talking about holdouts. That's what we do. Tree models and random forests. So logistic doesn't naturally incorporate interactions. You have to do the square to second. If you do, can anyone tell me just the full way of writing include interactions in a model? Which you can. It's going to take longer to run. If you're doing linear or logistic, how would you incorporate that in the model formula? Which you don't do that for tree-based models. How would you incorporate interactions? Dot raised to second right there. KP, great job. So dot means all variables. It's interesting in aggregate, sometimes squiggly tilde, twiddle, twiddle, dot raised to second. It's the formula format. Sometimes you can do with the aggregate dot tilde and then your y variable of interest like GPA. So I didn't even hit the twiddle. Dot twiddle. Oh, that is the twiddle? No. I'm going crazy. I'm going mad. I don't even know how to do my twiddles. Dot twiddle and then like something like GPA. And that would use it would use GPA as an X displaying all the Y variables. And that's how you can aggregate stuff a lot of times. Confused me at first when the aggregate did in a different order, but we don't have to worry about doing that with our tree-based models because as they split, they will naturally split within a variable. So they'll find some relationship that might only apply to certain cases of individuals. And that's what interaction means. It's like, if this is true about you, then the X variable works this way. But if this is true about you, then the X variable works this way. So the way in which the X variable works might depend on the other X's you've gone through in the tree, and that's what an interaction is. Let's check out the next question. Here we go. It is really anybody's game, and I love seeing Kahoots like this. This is neck and neck. People have been studying. I love it. Here we are. Which of the following tuner parameters does a singular tree use? A tree. This is a great review right here, and you should know all the names on the screen. We've got alpha, lambda, CP, and M trie. A singular tree. Alpha and lambda are used for what? You should know what all these values do, why we have them. Alpha and lambda do what? What are the alpha and lambda used for? GLM nets, that eliminates those, and then M trie is for the forest. So M trie is for forest, alpha and lambda. Lambda is going to be your regularization penalty, the amount of penalty you're doing for taking information. Alpha is going to be your mixing percentage of your lasso and ridge. M trie is going to be the amount of predictors that are tried at each node. And the complexity parameter, once again, and just a quick look at that again, is going to control how what. The complexity parameter controls for us how what we do the what. The complexity parameter is going to control for us how what we do the what. Good review of this right here. The complexity parameter, which we can tune, we can give it a grid of different values to be like, give it a shot. Do different ones. Just try all those. There's my complexity parameters over there, and just give them all a shot. All these are controlling right here for us is a singular tree, right? Well, so this is a singular tree, and the complexity parameter controls how what? Here's a hint. Big, small. So the complexity parameter controls what? It would look visually like this. The complexity parameter controls what about us? I'll do a little more up here. The complexity parameter controls what for us? So if we use a small complexity parameter is small. So this is the complexity parameter. How many splits happen? So it's kind of the return we need to do a split. So if the complexity parameter is small, then what will be big? If the complexity parameter is small, then the what will be big. So if the complexity parameter is small, because it's saying you only need a tiny, tiny return to split, then the tree will be big. Great job, Kale, right there. And great practice, everybody. The tree will be big. But if the complexity parameter is big, it's saying you need to get a lot to split the tree. So if we have a big complexity parameter, then the tree will be very small. And at some point, we really reach the what model. So this is kind of where you usually overfit over here. So overfitting usually happens with a very small complexity parameter, but then you're going to underfit or probably go towards the what model. Here's a hint. You go towards the what model when you're using such a large complexity parameter because your tree is barely able to split now. If you put in a very, very large complexity parameter, you're going to go towards the naive. If you notice right here, this is a visualization of a tree with like no splits. What you really want to do is find that optimum value, which is going to split just the right amount. So you're trying to find, where do we get the best return? And today, I think we were going through and we found something close to here to say, okay, this is probably where we want to split. Especially today in class, and I hope that helped a lot. Does anyone remember, as we were going through today in class, we built some trees, and then we found a tree that we could actually visualize that didn't look horrible. We went from some crazy looking trees. Here's our trees today in this class. We went from these crazy looking trees right here. We actually got a decent visualization on that. And we were like, we can't use this, to boom, some tree that we could actually put into our report. Doesn't look too bad, nice, clear, and sharp. And so this is what you want to go towards. So we were able to find a tree that worked just as well as our tree that worked the best. And we could actually include this into our report. And you'd want to include this. We said probably not this. Maybe this tree right here. This was a maybe on this tree. It's not as pretty, but it's readable. So readable works. This one I lean towards no. This one I lean towards yes. And this one, everyone should say yes. This tree is excellent. You should put this in your put that in your report and explain it to somebody. Which library builds those? Those are found under Rattle Fancy rplot. And check out today's class as we did. And Roberto, great questions right there. Those are from Library Rattle Fancy rplot. So Library Rattle Fancy rplot or Visualize Model in Reg class. Rattle's the library, and then Fancy rplot. Great questions. 100 points, Roberto. Thank you for asking. And when you're in class, remind me to mod people in class. Nice work. Here we go. Dandy Sea Lion. Oh, it's going to be a close game. You're welcome, Roberto. Here we go with the next question. How many models are created when using a GLMNet grid with alpha of 0.1, 0.3, 0.5, and lambda of 0.3, 0.5? This is redemption. How many models are created from this? How many models are considered? So remember, when you are doing the expand grid, you actually use all combinations of the values. Now, alpha is going to be the mixing percentage of our models when we're doing ridge and lasso. And then lambda is the amount of penalization we're putting on it. So when we do a higher lambda, we're doing more regularization and limiting the information we can take from the predictor X's. And so there are 3 and 2, which means there are 6. Good work, good practice. A lot of people getting this one right here. So there's 6 total because 3 times 2 is 6. There's 3 values there for alpha. There's 2 for lambda. I probably used a little bit different than a grid, but I want to write decently easy question than a bunch of zeros and hard to read sequences. So good stuff right there. How do we visualize or talk about the variables play the most importance in a model's predictions? Varimp. And we were doing that, Preston, good question today in class. Just really quickly right here, we were doing the varimp during class. And after you make your models, you can go in and look at the, got it this time, KP. Yes, that was shout outs to you right there. KP, that's awesome. Let's start some more points. Today in class, we made these tables right here. We talked about kind of what's expected. Has anyone after class made some tables, and was it pretty easy? Because I was hoping, I want to see some really great tables, take screenshots of them, put them in your report, make them nice and neat. Yes, you made it. Nice job, KP. That's what I like to see. So, and not too hard, right? So if you're trying to make some really nice tables of your output, check out today's class where we did it. Not yet, but I plan to. Nice. So I just want to, when I see, I'm like, we can make some really nice stuff here, get some great grades. And believe me, when I see people taking these ideas and using them, that's where, that's what I want to see. Because I always try to reward when I'm like, okay, they incorporated these ideas. I saw them up their game on this. And we're just trying to bring everyone to this like really great level and look at some really great reports. So that's got it. Please message me on Discord or email me if you can't get the data or it's not working as soon as possible. Final project coming up soon. Last 2 questions on the Kahoot. True, false. True that a complexity parameter of 0.02 considers a split and can lower impurity by this. Okay. So the complexity parameter is this. and we can lower the impurity at the split of this, it will split. Complexity parameter of 0.02, we can lower impurity by 0.03, we will split. Complexity parameter is 0.02, we can lower the impurity by this, it will split. True. What does complexity parameter means? I meant to say it is true that a complexity parameter... blaming the bright lights. If the complexity parameter is 0.02, that means we need to what? The complexity parameter is what? How true that... The complexity parameter is how much we have to achieve on the lowering of impurity. It's the minimum. Great job right there, Riley. That is some textbook right there. It's the minimum we have to achieve to do the split, right? So if we can lower the impurity by 0.03, we will split. Does that make sense right there, everybody? The complexity parameter is a bar saying you have to achieve this to split. And definitely check out the slides right here where we talk about it. We're adding it to the slide talking about if the complexity parameter is 0.02, will it split? And the answer is yes, it'll split right there on 2 because that is going to reduce the impurity by 0.04. So will it split right here? Well, if this is the complexity parameter, will we split? Let's pretend this is the complexity parameter. Will this split? Yes or no in the chat. Take a vote right now. If a little thinking music on there. Will this split with that complexity parameter? If that is the complexity parameter, will this split? Because what does the complexity parameter mean? As Riley said, it's the minimum threshold to split. It's the minimum threshold. So we look at this as a bar and we say, can we get above this bar? And if we get above this bar, we split. So the answer is most definitely yes, because we would split right here, because that's where we have the best lowering of impurity. And as long as we lower the impurity by this amount, what's going to be the problem with this tree? Going back to what we've been talking about a lot right here, what's the problem with this tree using a CP of this? What's going to be the problem with this? So here's the hint on the screen. We're going to probably overfit. We're going to build a super crazy big tree. Great job right there, Kevin, KP, Kirsten, and Yakui. 100 points. We're going to get a really big overfit tree using such a tiny, tiny, tiny complexity parameter, even tinier than those. So it just says, if you can do this tiny reduction, you get to split. So if we have a complexity parameter of 0.02 and we can lower the impurity by 0.03, we will split. Definitely true. I think this is the last one, and it really is anybody's game almost. It's a close game. We're going to find out who's going to win. Let's find out here. 2 more questions. I lie. The highest Gini coefficient is 5. I hope we've reviewed this a good bit. This was earlier review. We love doing some review questions at the end. The highest Gini coefficient is 5. Well, there are theoretical limits depending on the classes, but there's also pure limitations on how we calculate it. Great job. Does anyone just want to drop the highest Gini coefficient in the chat? That's worth 1,000 points for the class right there. Great job. It's 1. And for a 2-class summary, the highest Gini coefficient is what? With a 2-class summary, the highest Gini coefficient is what? Because it'd be 1 minus 1/2 squared plus 1/2 squared to be 0.5. So with a 2-class summary, you can only get 0.5 Gini coefficient maximum. So, and it's a measure of impurity of the leaves, because as soon as you start to go towards another way, it's less than 50% impure. So Gini coefficient does not go to 5. It goes between 0 and 1. I don't worry so much about entropy, and there are no entropy calculations on the test. Made sure of that. Who was the fastest fingers there? Ooh, Dandy Sea Lion. Super quick. But let's find out who's going to win. Rational Koala, you got a shot. Focus Cheetah, Sturdy Snail, you never know. It's a lot of people could possibly win this. Here we go. Last question is, which of the following explains what the validation does? What does validation do? I'm scared because this is a tricky one. How do we get generalization error? I bet someone clicked generalization error, so I'm already ready to tell you. How do we find the generalization error? No one said that? Oh my gosh. Well, we find the generalization error on the what? The generalization error is found where? How do we find the generalization error? How do we find the generalization error? How do we find the generalization error? We test our model on the what? So this is not validation, which is k-fold cross-validation. The generalization error is found by looking at the what? Generalization means how does it generalize? So generalization error would be found by checking the what. What data is going to get us the holdout? Exactly. So that is what protects against overfitting, is the actual holdout. So the holdout is going to investigate overfitting right here. So we can investigate overfitting by looking at the generalization error to see if we overfit. Used to estimate the model, that's actually the what data. What data estimates our model for us? Which you could say, but isn't this contained with, oh yes. But better way of saying used to estimate the model is the what data. We make this all the time. Used to estimate the model is the what. So what do we use to estimate the model? The train data, what we create the model from. That's why it's called training. So that's going to make our model. We're going to train the model right there. Great job in the chat. And then the estimated generalization error. The estimated generalization error is how we think it'll work on new data. And this is done via the what process. The estimated generalization error is done by the what process. How do we get this? And then that tells you the answer up here. The estimated generalization error is estimated by using what is called a pseudo holdout, doing the what process. The estimated generalization error is done by doing the what process. It ends with this right here. So how do we estimate the generalization error, which is what you see in your plots. If you notice that the plots right here, that's what you're getting over here. We should see a plot right here. It says generalization accuracy, but a lot of them will say estimated. I prefer it when it says estimated because that's what it's actually doing. It's estimating how it's working. So you're doing the k-fold cross-validation. The k-fold cross-validation is how we are estimating the generalization error, and that's why we call it validation, because it estimates how it'll do on new data. The generalization is how it actually works on new data. You know what time it is.
It's my time. Woo! Is it going to be Dandy Sea Lion? Dandy Sea Lion, where you at? Third place, Rational Koala. Woo! Where's the bunnies? Sorry, yak. Oh, I called it. I called it. It is Dandy Sea Lion. Great job. Make sure to email Brian, not me. I'm Tiny Brian. I'm out. Great job, Focus Snail and Sturdy Snail and Focus Koala. Woo!
Great job, everybody. Excellent work. Do people have any questions before we head off? Please email me if you're working with the data, if things aren't making sense. Make sure you've started your project as soon as possible. It's a large portion of the grade, and make sure you're explaining things. Make sure your executive summary. Has anybody, we'll end with this before we leave, has anybody been looking over the rubric? Since the final project is worth such a large portion of the grade, I wanted to make sure there was a rubric that detailed everything, every little detail. I wanted to make sure when you look at it, you're like, this is how I'm going to be graded. I am just following the rubric. Great job right there, KP. Do we get a two-side cheat sheet? Yep, front back cheat sheet. Exactly. Do we need to do a future research? There's the appendix at the end. You could, if you want, include some future research. I didn't include that on here. You could at the end kind of mention kind of where we're going from here. This is literally how it'd be graded. Great job, Kirsten, right there asking about this. This is literally, so the appendix is just kind of a reference thing. I put that on there as a 3 points. This is out of 103 points, but the assignment should be out of 100. So does it say out of 100 up there? It is out of 100 when I last looked. But there we go, points 100. So you can get up to 103 as I click through here. But very clearly outlining, and make sure when you're doing your executive summary, like if your executive summary is used as the report, you lose 10 points immediately. I'm worried about that for if it's the main majority of your report where you just have some graphics afterwards. Like if you give like the whole report and then you just put some graphics, then that's going to be 5 points. If you're missing key components, you'll get 10 right here. When you're describing the data, make sure you're giving graphics, make sure you're going through, summarizing the data, giving a talk about the data you'll be using, introduce the reader to the data. This reader's going to, as far as we know nothing about the data and be like, okay, what's going on with your data? What do we got going on with this variable here? What's your variables of interest? What's going on? Then we go to pre-processing of your data. Make sure to walk them through what was done. Maybe show them some before and after distributions. But be processing your data. Hey, Bayram, good to see you. Hey, Mr. Brian Stevens, before you leave, would it be possible to show exactly where Stetch 1 lecture located? Of course, yeah, we'll do that next right here. You got it. Thank you for asking. And then we got the methods being considered. So make sure you go over what kind of models you're using, kind of explain them a little bit. You don't have to go into great detail, but you probably need to talk about the different models and maybe list them and almost treat them as sections right there. Next, we go into the metrics and model selection. So you need to show how your models are doing, show comparisons, show maybe the grids that were used, show the output. Last, we want to go in here and interpret our results and get our final model and actually show how it's doing, predicted on new data, tested on the holdout. And then there you go. And big points right here. If you don't use your holdout and your train throughout, project uses full data sets to make models, or project focuses on predictions on the training data, you have to watch out if you're not using the holdout to do your predictions. That's an issue. Also, if you want, upload your RMD and I can maybe check to see if there's any issues. But sometimes I've had to check people's RMDs to make sure things were done. Usually that's to save you points. I'm not usually trying to check to take off points. I'm usually like, okay, they wrote the codes for these, right? Because sometimes you might describe something as like, this is how we did on the data. And I'm like, on the holdout, on the new data? Like, it doesn't say like when we made predictions on the holdout data, we saw that our model worked this well, or on new data the model hadn't seen, we saw that the model worked this well. So I'm usually double checking someone's RMD to see like, what else do we need to include? You can just think of this, and I really want to think of this just as a nice, clean, and quick bonus. You don't have to take it too seriously. If you include this, so I put present or missing, you can use RScript or RMD. Either one's fine. Awesome job, Preston. So Kirsten, it's as long as you just like kind of take it halfway serious and throw in a few like what you used, you'll be fine. I would focus 10, 15 minutes on that. There's no formatting. Just put in a nice appendix of what was used. Maybe like grab a thing inside a package. Yeah, it's meant to be a bonus. That's why I didn't really expand. It's meant to be pretty easy. Is this course in MSc or bachelor's degree? This is the bachelor's degree course, Roberto. Good question right there. This is the bachelor's course right here. Well, it's also given to graduate students too. Graduate students can take the 522 version of it, BZAN 522, and we're gonna go over here and go grab from our channel. So graduate students can take this course, or undergraduate students, and I love it. We get to do so many cool things, especially towards the end, and there's so much power in analytics. There we are live on YouTube still. Let's go over here to the playlist. So if you're looking for 201, I've got right here all the playlists, and probably a good place to start is probably, let's see here, all chapter review. This is a decent place to start right here. Kind of walking through the all chapter review. Let me drop this in the link for you here, Bayram. I would check out this playlist right here, the all chapter review, and you can always post questions under the video. I try to reply to whenever people put questions. See, we don't get a lot of questions, but you can add a question. I would start with the all chapter review. You could also, I'm trying to think of another really good playlist. There's some of the old lectures are unlisted and stuff. You're welcome, Roberto. And trying to think what else would be good. What else would be good? Visualization assignments. Test 1 speedruns are pretty cool. So speedruns are like shorter versions of the videos. So here are speedrun of test 1. So this is just test 1 material right there. And there's speedruns of the chapter. So kind of some fun stuff.
Epic Stat Tool 1 speedruns of statistics. Brian Stevens versus Chapter 1. Stats start here. Begin.
Awesome. Well, yeah, glad to help out, Aaron. Where are you taking statistics? Well, I shouldn't ask. What topics are you covering right now? If you mention a topic like the normal curve, or are you doing correlation right now? What topics are you covering in statistics? Like normal curve, correlation, t-test, chi-squared, doing those ring a bell, pie charts, bar charts, summarizing data, sampling methods. If you go to the channel, a lot of times you can search on the channel by just clicking on where's the channel. And there's better videos like maybe for studying stuff. But if you go here and type in like t-test or something, you'll probably get a lot of office hours, called a lot of office hours. There it is, the t-test right here. So I made a video. Our next test that we want to talk about here is a one sample means test, one sample t-test. How fast you can run a mile. Just look crazy. So I go through, mark the notation right there and talk about it. But this is the one sample t-test. Gosh, this is almost 3 years ago now. Or is it? No. Yeah, 3 years ago. It was 2019, I think. It was winter 2019. Yep. And so yeah, just going through, talking about the data right there. So long ago, 3 years ago, almost 3 years, 2.5 years ago. But let me know if you have any questions. I go through and explain it. Oh, yeah. Oh, no, yes. And well, if you have questions, does the project, is it similar? Yes, but do remember, this is like the big one. This is the super important big one that we need to make sure we have pretty much. It's the big one. I want to make sure we go through. And so what are we going to do to get a great grade on it? How are we going to get a great grade on it? What are we going to do? I'll go over to the main screen right here. What should we do to make sure we make a great grade? Like, one of the things we can do is make sure when we're doing it, everything is led up to this. We're going to follow the what. Follow the what. Follow the what. I would definitely follow and look at it and make sure I'm meeting those guidelines that I put on there. Follow the rubric. So as you're going through, making sure you're doing it, you don't want to be brief. You don't want to use your executive summary as your report. You don't want it to be too short. You want to write your report, then make the executive summary. That's some serious statistics stuff, like the PhD guy with the ukulele on YouTube. Oh, there's PhD guy with the ukulele. That's pretty cool right there. Well, thank you, Roberto. Yeah, we like to have a little fun here. We'll end with some memes. With that, I'm supposed to move to the side, but it doesn't do that anymore. I need to fix that. The move transition. It's supposed to just shift over to the side. The future research, you could include it. I didn't put it there. I was just running out of room and it wasn't in the instructions, so I didn't include it. You could. I'm not going to count off if you don't put future research. But make sure you write your report and then summarize it. So make sure to do that. So, yep. Yeah, and just make sure you write your report and then you executive summary it. So you want to write your full report and then turn it into an executive summary. I think a lot of people have tried writing the executive summary first. You write a report and then you say, I need to give a summary of this. And I think that's where people usually don't write a good executive summaries, because they start writing executive summary as the report. It's like, no, you write a report and then you turn executive summary. So there's summary like the normal essay conclusion. Well, but it's, remember, the executive summary is the whole report. So you take your whole report that's maybe like 8 pages and you condense it into like a page-ish. So the report, all the key findings, the models used, the data analysis, everything would be without graphical analysis. You don't just take the words you wrote and just put them on the first page and remove pictures. You think about, how could I communicate these ideas to executives in a quicker fashion? Like, you just, it can be written a little more easily because you're grabbing the big ideas of what you've done, and you should walk them through what was done in the project. Basically, someone should know what your project is and all the key findings and what we're going to do from the executive summary. So yeah, let me know if you have questions. With that, it's time for some dinner. Bye for now, everyone. Bye.